What specific problem does the Nemotron-H model aim to solve in terms of inference efficiency and computational resource utilization?
The Nemotron-H model addresses the inefficiencies associated with traditional self-attention layers in large language models, LLMs, which require linear computation and memory scaling with the number of tokens processed. This limitation can hinder overall model intelligence and inference speed. By incorporating a mixture of Mamba-2, self-attention, and MLP layers, the Nemotron-H models achieve sublinear or constant compute and memory requirements, significantly improving inference efficiency. For instance, Nemotron-H56B base demonstrates up to 3 times higher inference throughput on NVIDIA H100 GPS compared to traditional models, particularly with longer input sequences. Additionally, the use of FP8 pre-training and the mini-puzzle compression technique further enhances resource utilization, allowing for effective deployment on GPUs with limited memory.
How does the proposed method, the Nemotron-H model, work? Illustrate the architecture and training methodologies step by step, including details on the mixture of Mamba-2, self-attention, and FFN layers.
The Nemotron-H model architecture integrates a mixture of Mamba-2, self-attention, and feed-forward neural network, FFN layers to enhance efficiency and performance. Specifically, for the Nemotron-H-8B model, it consists of 52 layers, with only 4 self-attention layers, approximately 8% of the total, while the remaining layers are evenly split between Mamba-2 and FFN layers. The architecture mandates that the first layer is a Mamba-2 layer and the last is an FFN layer, ensuring that self-attention layers precede FFN layers, akin to standard transformer blocks. In terms of training methodology, the models are pre-trained on vast datasets with Nemotron-H8B base trained on 15 trillion tokens and Nemotron-H56B base on 20 trillion tokens, utilizing a layer-wise mixed precision approach where most layers operate in FP8, except for the first and last 4 layers which are in BF16. This training process employs a phased data blending strategy, initially promoting diversity and later focusing on high-quality datasets, which significantly improves model performance on downstream tasks. The combination of these architectural choices and training strategies allows the Nemotron-H models to achieve state-of-the-art accuracy while improving inference speed compared to traditional transformer models.
Can you provide a simple example that demonstrates the inner workings of the Nemotron-H model during inference, including how it handles long input sequences?
The Nemotron-H model utilizes a hybrid architecture that combines Mamba-2 layers, self-attention layers, and feed-forward networks, FFNs, to enhance inference efficiency, particularly with long input sequences. For instance, during inference with a long input sequence of 65,536 tokens and generating 1,024 output tokens, the model benefits from the constant computation of Mamba-2 layers, which contrasts with the linear computation required by traditional self-attention layers. This design allows Nemotron-H to achieve up to 3 times higher inference throughput on NVIDIA H100 GPS compared to other models like Qwen2, 5-7B, and Llama-3.1-8B. Additionally, the reduced memory footprint from Mamba-2 layers enables the model to handle larger batch sizes, further increasing efficiency. Overall, this architecture allows Nemotron-H to effectively manage long contexts while maintaining high performance in generating outputs.
What are the theoretical or practical benefits of using the Nemotron-H models over traditional transformer architectures in terms of speed and computational efficiency?
The Nemotron-H models offer significant theoretical and practical benefits over traditional transformer architectures, particularly in terms of speed and computational efficiency. Firstly, they utilize a hybrid architecture that incorporates Mamba-2 layers, which provide constant computation as opposed to the linear computation required by self-attention layers in standard transformers. This design results in up to 3 times higher inference throughput on NVIDIA H100 GPS when generating longer sequences, such as 65,536 input tokens and 1024 output tokens. Additionally, the reduced number of self-attention layers in Nemotron-H models leads to a lower memory footprint, allowing for larger batch sizes during inference, which further enhances efficiency. Overall, these improvements enable Nemotron-H models to generate output tokens significantly faster, 4 times more than QWEN 2.5 to 72B and LLAMA3, 1 to 70B, and 19.6 times more than LLAMA3, 1 to 405B, demonstrating their superiority in both speed and computational resource utilization.
How is the performance of the Nemotron-H models validated? Discuss the experimental design, datasets used, and metrics for performance evaluation.
The performance of the Nemotron-H models is validated through a series of evaluations on common benchmark tasks, including mathematical reasoning benchmarks like GSM-8K and Math, as well as general reasoning tasks such as OpenBook QA and PIQA. The experimental design involves comparing the Nemotron-H models against existing state-of-the-art transformer models, ensuring that both model types are trained on the same datasets for a fair comparison. The datasets used for pre-training include a large corpus of high-quality curated data, synthetically generated data, and diverse sources such as web crawl, math, code, and academic texts, amounting to trillions of tokens. Performance metrics focus on accuracy across various tasks, with specific attention to how well the models perform on tasks like common sense understanding and reasoning. The results indicate that Nemotron-H models achieve comparable or superior accuracy relative to similarly sized models, with Nemotron-H 5.6B base outperforming LLAMA3 1 to 70B on 16 out of 17 evaluated tasks, demonstrating their effectiveness in real-world applications.
What limitations or drawbacks does the Nemotron-H model have, particularly regarding specific use cases or computational constraints?
The Nemotron-H model, while demonstrating state-of-the-art accuracy and improved inference speed, has certain limitations. One significant drawback is its reliance on a mixture of Mamba-2, self-attention, and MLP layers, which may not be optimal for all tasks, particularly those that heavily depend on self-attention mechanisms. Additionally, the model's architecture requires substantial computational resources. For instance, the Nemotron-H 5.6B base model's weights alone demand approximately 29.5 GB of memory, which can limit its deployment on hardware with lower memory capacity, such as single NVIDIA RTX 5090 GPUs. Furthermore, while the FP8 pre-training approach shows promise, it may not generalize well to smaller models, as results with smaller parameter counts did not replicate the performance of larger models. Lastly, the model's performance on specific benchmarks, such as the Winogrande task, indicates that it may not consistently outperform all existing models across all tasks, suggesting variability in effectiveness depending on the use case.